So in this video, we're going to explain what is that L quantum number. So on the last video, we had come down to separating out the R's and the thetas, and we said that was a constant, and this was a constant, and we ended up solving for that constant. It was L times L plus 1, where L was 0, 1, 2, 3, and so on. So then we had to solve this equation. Later we're going to have to set this equal to L times L plus 1 to solve the radial part. But this, we said, was a special differential equation, a Legendre differential equation, and the solution were, these thetas were called Legendre polynomials. All right, and there's an infinite number of them, and they're all orthogonal to each other. And then when we combined those with the phi's, both the thetas and the phi's, that gave us these y's, which we called spherical harmonics. They were now we're talking about both theta and phi. It's kind of gives you the ripples on the surface of a sphere. That's what these do. And the higher the number, probably the more ripples you have. Here's just one in particular, 1 plus minus 1, L equals 1. I put a list of them on there before. And we said L can be 0, 1, 2, 3, so on. But M sub L can be 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. So M sub L can't be bigger than L. That's where they kind of get stopped right there. And what we can say is every function that you can think of on the surface of a sphere can be written as a bunch of y's. That is, any function of theta and phi, it doesn't even, can be written as the sum of a bunch of y's. Just kind of like we said for Fourier series, any pattern we could write as an infinite sum of sines and cosines. Well, we could do this same sort of thing here. It doesn't even have to be a function of theta and phi. It could be a function of x, y, and z, because we can turn our x, y's, and z's into this. We would just get rid of the r part because we're only looking at on a sphere, and that's where r is a constant. So if we had something like, I don't know, let's just say we had psi was equal to the square root of 3 all over 4 pi sine theta times cosine phi. And I ask you, what is that in terms of just the y's right here, in terms of your y's? Well, you notice when we listed all of our y's last time, so I want to write this as a bunch of y's, all of our y's didn't have any trig function with phi. They were all e to the plus or minus some number times I phi. So what I should do with this one is turn it into e to the I plus e to the minus I over 2. So this is just the square root of 3 all over 4 pi sine theta, and then just turn your phi parts into, I could turn that into exponentials, e to the I phi plus e to the minus I phi all over 2. I guess I can put the 2 anywhere right here. Let's say 2 right there. Actually, let me put the 2 inside of here, and then it would be 16 because I'd have to square it to put it in there. So we'll put it in there, make it 16. Okay, so I can write this as the square root of 3 over 16 pi sine theta e to the I phi plus the square root of 3 over 16 sine theta e to the minus I phi. Well, you'll notice I wrote down just the 1 plus or minus 1. You'll notice the only difference here is this one has an extra square root of 2 in the bottom because this has a square root of 16. And you noticed right here, for when this is plus, this one should be minus. So if I just took this minus and brought it over here, this first term right here just looks like minus 1 over the square root of 2, y, 1, 1. You notice y1 plus 1, that would make this a minus. That's why I need the minus in front. And this would have been a plus, just what I had. Plus, this term, there's a pi there. 1 over the square root of 2, y1 minus 1. So I can write them in terms of y's right here. It makes it a lot easier if you're dealing just with y's rather than this. So any function I could write in terms of that. Now I could plot that out to see what it looked like on when I went between the donuts and the snowmen. If I wanted to see what the probability here was, I'd have to multiply this times its complex conjugate. So you'd have to do a minus 1 over the square root of 2 y11 star plus 1 over the square root of 2 y1 minus 1 star times it without the star right here. Minus 1 over the square root of 2 y11 plus 1 over the square root of 2 y1 minus 1. And that would give me another picture. This one's kind of a famous one chemically wise. This one is actually, sometimes they call them PX right here, PX. And it looks like the snowman, but he's on his side along the x-axis. So our snowman before was along the z-axis, but this one is kind of a snowman along the x-axis. They call it PX. There's also a PY where you have a snowman along the y-axis too. And you know, if you start putting these things together, you can start looking at what are called orbital hybrids. Orbital, especially for carbon atoms like methane or ethane, or orbital hybrid orbitals. Orbitals. Now, if you go onto Canvas, go into Files, Canvas, go into Files, I put in some pictures of some different sp orbitals right here. You might just go ahead and look at them right here. So those are just, you know, so there you might recognize some pictures from chemistry. Okay, so what I wanted to talk about now is what is the L quantum number? What is that right there? Well, we already said what Lz was. Lz is this. This is the L. I should put a Z there. That was the Z component. So the Z component of my operator is minus IH bar partial with respect to phi. Okay, well, what about the Lx? What does the Lx look like? Not so nice. The Lx is not so nice. It's actually IH bar sine theta partial with respect to theta plus cotan theta cosine phi partial with respect to phi. Okay, it doesn't look real nice right here. You probably don't use that for any operator. It's probably easier just to call that direction Z and use the Z right there. Now we can, what about L and the Y? L and the Y. So we're getting these the same way I got that right there. But L and the Y would be, again, it's not a very nice one either. It's IH bar minus cosine phi partial with respect to theta plus cotan theta sine phi partial with respect to phi. So again, these aren't very good right here. Not only that, if I tried to do Lx on my psi to get lambda psi, I would have different eigenfunctions. These would be different eigenfunctions than Lz on phi equals lambda phi, which means I could not know both Lx and Ly at the same time, just like we couldn't know Sx and Sy at the same time. So we don't even want to use this because this is a messy one right here, and these aren't even the these are different eigenfunctions. But what happens if we were to find L squared? The operator of the total angular momentum squared. Well, that would just be this squared plus this squared plus this squared. That would be Lx squared plus Ly squared plus Lz squared. So I'd have to square this, and square this, and if you add them up, it ends up being minus h bar squared 1 over sine theta partial with respect to theta sine theta partial with respect to theta plus 1 over sine squared theta partial squared with respect to phi squared. You might say, well, that doesn't look nice, but it really isn't so bad right here, because remember my wave function, psi, we said it was r and then theta and phi, but the theta and phi's are just the y's. So there's my psi right there. Now, you notice we have this differential equation right here. This differential equation. Remember, we put this thing all on the other side. And when we put it all on the other side, we ended up with, this was a positive term right here, and we multiplied by phi. So we put that in this side, we multiplied by phi, and we ended up with 1 over the sine theta, and then we had d theta of sine theta. Sorry, sine theta, d theta, plus, now again, we put this on the other side. We had the L times L plus 1 times the big theta that we multiplied through. So we got L times L plus 1 times big theta, but I'll factor it out. And then we also brought this term over, so it's minus m sub L squared all over sine squared theta, big theta, and that equals 0. So that's what I get when I just solved, again, this equation right here. Remember, we want to get the meaning of what this L is right here, L. Well, suppose we were to multiply everything through by my big phi. So, because what I want to do is, remember, y was equal to theta times big phi, right there. So what I could do is, I could just replace these, everything I'm taking the derivative of, this and that, I could replace it with my y's, big Y, and turn all my derivatives into partial derivatives. Why? Because then we're just taking the derivative with respect to, we're just taking the partial derivative. Or if I just multiplied everything through by big phi, let me just multiply everything through by big phi. I'll just put it like this. I can put it right here. I can put it right there. Theta phi, but turn that into a partial with respect to theta. Okay. And I can do the same thing over here. I can make that, since I'm multiplying by a phi, I can just make that theta phi. So you notice this just becomes a y, and that just becomes a y. So we end up with 1 over sine theta, and all my derivatives become partials, because we don't want to take the derivative with respect to phi. Derivative partial with respect to theta of sine theta, partial with respect to theta of y, plus L times L plus 1 minus m sub L squared all over sine squared theta times y equals 0, where the y's are the L and m sub L's right there. Okay. Well, you see this, before we said m sub L squared is just minus this. So I'm going to replace m sub L squared, actually m sub L squared phi, actually what do we have? We have 1 over phi. Over there we had 1 over phi, d squared phi, d phi squared is equal to minus m sub L squared. Okay, if I were to multiply everything by phi here, phi, is that the way I want to do it? Yeah. Multiply everything by phi, so you got d squared phi d phi squared is equal to minus m sub L squared big phi. And now let's put in the theta into here. If we put this theta into here and put the theta in there, then they become y's also, except the derivatives have to be a partial derivative. So the second derivative of y with respect to phi squared is equal to minus m sub L squared y. So we just put the theta in both ends of those. Okay, so now right here, you'll notice we have a minus m sub L squared y right there. So I have a minus m sub L squared y. I can replace this term right here, this times this, at least this term, with a second derivative. This would be a plus, second derivative with respect to phi squared with the sine squared on the bottom. So let me rewrite this again. So we got 1 over sine theta d theta, sorry, we're doing the bottom one, partial with respect to theta, sine theta, partial y with respect to theta, plus, well, I'm going to take this term and put it on the other side. So on the other side of the equal sign here, I'm going to put minus L times L plus 1y. Minus L times L plus 1y. And then this term right here, remember, we just said that that term is this term right here. So it's minus, no, it becomes a plus because there was a minus there. It becomes a plus 1 over sine squared theta partial squared y with respect to phi squared. Okay, so that's what that equation became. Now you'll notice this equation right here. If I were to act L squared on y, it would give me almost this right here. Matter of fact, let's multiply both sides by minus h bar squared up there. So if we multiply both sides by minus h bar squared, and also over here by minus h bar squared, then what do we end up with? We end up with minus h bar squared. How about, I'm going to write it like this. 1 over sine theta, partial with respect to theta, of sine theta partial with respect to theta. I'll pull the y all the way out of everything. Plus 1 over sine squared theta partial squared with respect to phi squared on big Y. That's what I'm taking. And that equals, multiply that through, that is equal to h bar squared L times L plus 1 Y. Okay, so if we look at this equation, this is the same thing as this. This is my L squared operator. So it looks like L squared operator acting on Y is equal to h bar squared L times L plus 1 Y. This is my eigenvalue, eigenfunction equation. That means that this must be the angular momentum squared. So angular momentum squared, at least the magnitude, angular momentum squared is just h bar squared L times L plus 1, or the magnitude of the angular momentum, or it has just a magnitude of it, is h bar times the square root of L times L plus 1. So that's the meaning of the orbital quantum number. It tells you the total angular momentum of the orbiting electron. Okay, and we already said what L can be. L can be 0, 1, 2, 3, and so on right here. So this is the total angular momentum. So all we can get, and you'll notice it still uses the same eigenfunctions that the LZ worked. Because when I do LZ on Y, the same eigenfunction, I get m sub L h bar Y. So I can know both the total angular momentum and the z component without it scrambling them up. So I can measure the z component and the total. That's all. I can't measure the x or the y. So let's look at it for L equals 0. What's the total angular momentum? Well, if you plug in 0 here for L, you get 0. So the total angular momentum is 0 for that lowest state. And the L sub z better be 0. Also, we can't have a z component if the total angular momentum is 0. That's different than Bohr said. Bohr said, remember, he said the total angular momentum was nh bar. And where n started at 1. So he said the smallest was 1 h bar. No, it could be 0. If we look at L equal 1, well, that means the total angular momentum can be h bar times 1 times 2, so that's the square root of 2h bar. And the LZ component, remember LZ is equal to m sub L h bar. The biggest it can be, remember m sub L can be 1, 0, or minus 1, so LZ can be h bar, 0, or minus h bar. That's all it can be. Which tells me that when we look at if we were to plot this thing out right here, the total length of the vector has to be this long, and the z components are these long. So if you were to draw, let's say a sphere where coming out to here is the square root of 2h bar, but the z component can only be h bar. That would mean that the z component is just h bar, or it can be 0. Well, that would mean you'd have to be over here like this, or it could be minus h bar. So it's going to be down here, where this is minus h bar. And if we wanted to get this angle right here, this angle, well, we can see that the cosine of this angle is this side over that side, which is 1 over the square root of 2, which is 45 degrees right here. So when we drew this, we had our wheel. So our orbital angular momentum, for this case right here, it's pointing out like that. So it's going around, there's the orbital angular momentum right here. But it can't stay like this, and so what it does is it precesses around like this, so that this z component always stays fixed and the angular momentum stays fixed. This other case would be like this and going around like this. And the third case would be going around, going around like that. So you can see almost that space is kind of quantized because you can only be in certain configurations right here. Well, let's go to a higher one. How about L equals 2? Well, that means that this is 2 times 3, which is the square root of 6h bar. So that's the length of it. But the z component, L sub z, can be 2h bar, h bar, 0, minus h bar, minus 2h bar. 2h bar is less. It could never be bigger than this. The z component of a vector can't be bigger than the magnitude of the vector. So for that case, the length, the sphere, think of the sphere or whatever out at 6 square root of 6 pi, square root of 6 h bar. But the z component can be 2h bar, so maybe I should bring it up here a little bit higher. So it's at 2h bar. 2 is probably about right there. So there's 2h bar, and there is the square root of 6h bar. Or it can be at 1h bar, which is over here, where this is 1h bar. Or it can be 0, or it can be minus 1h bar, or minus 2h bar. If you wanted to get this angle right here, we can see that the cosine theta is 2 over the square root of 6, which I think is 35 degrees. It's 35 degrees. And this other one would be 1 over the square root of 6. That's like 65 or 66 degrees right here. And then there's 90. And then these would be symmetrically on the other side. And you can see as we get more and more, as this grows, there's going to be a lot more in here. And if you go, if L went off to infinity, then this would just be continuous, more classical right there. Okay, so you get, so now that we have these definition of both little l and big L, well, suppose we have a state, say y sub, it's a mixed between some of these different y's. I'm just going to make this up. It's 3y11 plus 4y73 plus y71 all over the square root of 26. Okay, so this is made up of a mixture of the y11, L equal 1, m sub L equal 1. This is L equals 7, m sub L equal 3, y L equals 7, m sub L equals 1. You can see that this is normalized because this is 926 and 1626 and 126. So it's normalized to 1. Suppose you were to measure L sub z on this system. What are the possible values you could get? So if you were to measure L sub z, what are your possible values you can get? Well, L sub z is right here. And so for the first case, remember m sub L is the number up top. So this thing can give you what? An one h bar. This one could give you 3h bar, and this one can give you only 1h bar. So there's two possibilities. You can either get 1h bar, or you can get 3h bars. Right there. Now, those are the possible values. What is the probability of each one of these? Well, the probability of this one is whatever is in front squared, so it'd be 16 over 26. This would be 16 over 26. That would be the probability. So let me put it underneath here, probabilities. And the probability of getting this should be the rest, 10 26. It'd be this guy and that guy, because they're both ones. 9 26 and 1 26, which is 10 26. Okay. So if I wanted to get the average of LZ, I don't have to sandwich it all in and do all that stuff that we did before. Didn't we just say it was the probability times the value? So it'd be 10, you have a probability of 10 26 of getting 1 H bar, plus 16 26 probability of getting 3 H bar. Okay, and so what does that give you? It gives you 48, 58 H bar over 26, which would be 19 over 13. No, that's 29 over 13 H bar. So there would be your average L. What about if you wanted to measure L, the total angular momentum? The total angular momentum. What could you possibly get? The values you can get, well, that depends on the bottom number. That's given by this, L times the square root of L times L plus 1. So for this one, you can, when L is 1, you get 1 times 2, you get the H bar square root of 2. So one value you can get is square root of 2 H bar. And then the only other value you can get is when L is 7. When L is 7, that's 7 times 8, that's a square root of 56 H bar. Okay, and what are the probabilities? Probabilities. Well, the probability of getting the 1 is just this guy all by himself, which is just 9 26. So this is 9 26. And the other one must be the rest of it. It's 16 26 and another 1 20, 17 26. 17 26. So if I wanted to get the expectation value, or the average L for that state, it's just what you get times the probability. So it's the square root of 2H bar times 9 26 plus the square root of 56H bar times 17 26. Okay, I guess I could pull out some stuff. It'd be the square root of H bar over 26. I think I can even pull out a square root of 2 out of it. Well, we'll leave it. H bar over 26. And then it'd just be 9 square root of 2 plus 17 square root of 56. Whatever that is. That would be the average you get for L right there. So you could, when you put them in this form, it's really easy to find what you would get, the averages, the expectations, and so on, right here. Okay, last thing, and that is, you notice when we did the infinite well, the last thing we did with the infinite well, we looked at spontaneous emission. And we said when the state dropped right here, it might have started in this state, but the vacuum of space perturbed it enough to put it into a mixed state, and then it dropped and came down to this lower state. And we had some dipole moment, which was P. It had some initial state and some final state on it. And I think we defined it as the integral of the initial state star x final state, dx. And if this number was big, then this could happen, and the bigger it is, the quicker it happens right here. And if this was ever 0, we had selection rules, and it could never happen. Well, we're going to do the same thing here. We haven't developed what the selection rules are for R, but we can still get it for L and M sub L. And if we wanted to do it for the L right here, what would we do? We would say, the only thing is, over here we would have to put in, we'd have to integrate over thetas and phis. D theta, and, well, let's go phi here. D phi, d theta. And then we'd put in our y star. We would be using our y star. And then remember, anytime you're integrating over theta, you have to put a sine theta in, so there has to be a sine theta just for the volume element. Then you also get, now x. I don't want to put in x, but we know what, actually let's do for z. I'm going to put in, what we're going to do, I'm just going to not use x, we'll use z first. I could use z, I don't have to use x. It's a dipole along the z, dipole along the x would be along the x direction. And remember, z was r cosine theta. So I'll just put in, we don't care about r, so I'll just put the cosine theta in, and y, okay, and that right there. And one of these will be the initial state, that is L initial, M sub L initial, and L final, and M sub L final. And now if we integrate this thing and look at it for different, make a whole table like we did before, if we ever get zeros, it means that it could never make that jump. Well, I did make that table right here. Matter of fact, if you go onto Canvas and to go into something called Spherical Harmonics Lab, you can see these tables. But let me just write in what I got for the table. So here I said, well, there's two things that are varying. There's L varying and there's M sub L varying. I don't want to vary too many things at one time. So I said, let's keep the M initial equal to 0 and M final equal to 0. And let's just see how it depends on the L quantum number. So I'm just going to make a whole table of different L's right here. So this is the initial L. Let's say 5, 4, 3, 2, 1. And I don't want to start at 0 because you can't drop, if you start at 0. And then the final up here, L final, this one can go to 0. 0, 1, 2, 3, 4, and 5. 4, we'll go higher. And when you make this table, you'll see this table that everything here is zeros. Except for this last row right here. These are non-zero. Matter of fact, this was something like 1 over the square root of 3. It doesn't. 2 over the square root of 15. 3 over the square root of 35. ... These are the only ones that are non-zero, which means that if you're in the initial state 1, you can only drop to 0. If you're in 2, you can only drop to 1. That's it. If you're in the 3, you can only drop to 2. So that means your delta L has to be 1 right here. I should say plus or minus. It could probably be plus or minus 1 right there. It could be 1 if you're absorbing. Remember, what is L? L is related to the total angular momentum. And you'll notice when this thing drops, what are we getting rid of? We're getting rid of a photon. Well, a photon carries angular momentum. Well, if the atom loses 1 unit plus delta L is 1 unit of angular momentum, that must mean that the spin of a photon is 1 h bar. So that tells me that the spin, remember, you have to get rid of this. If you're getting rid of angular momentum, it's got to go somewhere. Tells me that the photon that was emitted has L equal to 1. And didn't we say that before? We said a photon was a boson. It had an integer spin. And so this more or less shows you that you have to, if the photon has an integer number of spin, if it's going to carry it away from the atom's got to lose 1 unit of spin here. Now, we also, on that last one, we showed, you saw some movies where the wave function wiggled back and forth. When it was in the transition, when it was in this transition, it kind of wiggled back and forth. Well, I have a movie that you'll see on the screen that also shows this wave function wiggling back and forth. It'll look something like a balloon going back and forth through a ring. You know, at first it's up here, and then it's squeezed down, then it's down here. It's going back and forth. And since this is just the Z dipole, this is actually due to polarization, linear polarized light. This is going to give you linear polarized light. Okay, so since this thing is just going up and down right here, you're going to get linear polarized light anytime these two are the same right here. Now, that tells you the selection rules for L. What about the selection rules for M right here? Well, what you can do is you can say, well, let's go back and make another table just like this, except since you have to drop by 1, I said let's let L initial be 3 and L final be 2. Okay. And now let's vary the M's. Okay, and so now make a table of possible M's. The final M and the initial M. And you're going to get, you're going to get 2, 1, 0, minus 1, minus 2, 2, 1, 0, minus 1, minus 2. And when you do this, fill in this entire grid here, you're going to get them all 0 except for this center diagonal. This is the only one that's non-zero. You'll see it on that. If you look at that spherical harmonics lab, non-zero, which means that you only get this when there's no shift. Actually, I should have made this backwards. Minus 2, minus 1, 0, 1, 2. When you go, so if you're going from minus 2 to minus 2, minus 1 to minus 1, 0 to 0, 1. So this thing says that the change in M sub L has to equal 0. So there's the selection rules. The M sub L can't change. But again, we only looked at it for the Z here. Remember, there are other things we can put besides Z. You could have the X in there, and you could have the Y in there. When you put the X in there and the Y, they both do the same thing, but they give what they give you is when you put an X in there, let's say an X, what you're going to get when you do this, that stays the same, but what you get over here is you get that 0, but you get non-zero on either side. Which means that these two would mean that M sub L could grow by 1 or drop by 1. So there's actually a second selection rule for the M sub L. It can also be plus or minus 1. And when this occurs, when you drop and your M changes by 1, then you get what's called circularly polarized light. And I have a second movie on there showing you what happens when you drop by 1 when you're in this mixed state, and you'll see the wave function kind of circulating around, and that would be right circularly polarized. When it goes the other way, when it's minus 1, it does the left circularly polarized. So this now tells us, so far we have selection rules for M sub L, and for L, when we get to the hydrogen atom, now when it starts making transitions. Okay, and so this is our angular part, thetas and phis, and the last thing we have to do is the radial part, which is this. We have to set equal to that and solve for R. Then we can start putting in the potential for different things. We can put in the potential for the hydrogen atom. Right now, we can do it for any central potential right here, but then we'll put it in, and hopefully we'll get the energies for the hydrogen atom and the full wave function. Remember, the full wave function is this, or with the y here, and then we can add that to it. We can get actually the entire wave function for the electron in the hydrogen atom. Okay.